Welcome to another example of rigid body plane motion. You're designing a frisbee launcher to launch a 40 centimeter diameter 0.6 kilogram frisbee that can be modeled as a flat circular disc. Suppose you wanted to have a linear acceleration of 20 meters per second squared and a 50 radians per second squared angular acceleration. The question is, what should forces F1 and F2 be to produce these accelerations? Observe that I already drew a free body diagram of the frisbee. Let's say this is the free body diagram, and on the right side I have the mass acceleration diagram. This is force F1, force F2. This is center of the frisbee, point C. The unbalanced forces cause an acceleration, let's say in y direction, so I have MAY, and they produce a rotational acceleration which causes a vector I alpha in the direction shown. Let's choose this point and give it a name like point A, and we have a mass of 0.6 kilograms, a diameter of 40 centimeters, therefore the radius is 0.2 meters. Angular acceleration, alpha is 50 radians per second squared, and linear acceleration AY is 20 meters per second squared. So observe that we are interested in forces F1 and F2. Clearly, one key equation is net force in y direction equals to MAY. Another equation is a moment equation. I choose counterclockwise to be positive and write moment of all vectors about any point such as A on free body diagram must be the same as moment of all vectors about the same point for mass acceleration diagram. Observe that when you take the moment equation, you can choose any appropriate point, such as mass center C. In fact, the solution that you see on the PDF version of this problem uses net moment of everything about mass center C. But I want to show you another way of doing this to give you a better understanding of the different options that you can use to tackle a problem. Basically, I have two unknowns, F1 and F2, that I'm interested in finding. This means that from a mathematical point of view, I need two equations. So two equations, two unknowns. But observe that if I take moment of the forces about point C, I have an equation that has two unknowns, F1 and F2. And this is what you see in the PDF solution. So I want to show you an alternate way of doing this. If I take moment of everything on free body diagram about point A, observe that F1 is eliminated from this equation, and F2 is the only force that has a moment about point A. Therefore, using the moment equation, I have 2R F2 for the left side diagram equal to moment of everything about the same point A, which is sum of I alpha, which is already a rotational load, plus moment of MAY, whose distance is R times MA sub Y. With this approach, I have one unknown. So if I plug in the numerical values, 2 times R, or the diameter is 0.4 meters, times F2 equals to I. Recall that I is, let's see, 1/2 of mr squared. So I have 1/2 of mass, which is 0.6. Radius is 0.2 squared times alpha, which is given as 50, plus radius is 0.2, mass is 0.6, AY is 20. I'm using primary units. All values are numerically known except F2. So solving this equation for F2, it gives us a value of 7.5 newtons. So that's one of the two unknowns. Then if I go with this equation, the force equation, in y direction, I have the following. I have F1 plus F2, which now it is known as 7.5, equals to m 0.6 times AY, which is 20. So this gives us F1 equal to 12 minus 7.5, or F1 equal to 4.5 newtons.